Physics is not just a strategy for solving problems. It reveals aspects of the fundamental truth of our universe. Today, I want to talk about one part of that truth, that every person is attractive. In fact, every person attracts everyone and everything else to some degree. Now that you've had your daily confidence boost, let me explain the principle of universal gravitation. To most of us, gravity is the most familiar of the four fundamental forces. It gives us weight, binds us to the Earth, and holds the Earth in its biologically friendly orbit around the Sun. However, there is more to learn about this force. It has a few surprising aspects that are not just cool to know, they are essential for a deep understanding of this universe we inhabit. That's why I'm going to discuss Newton's interpretation of gravity, the law of universal gravitation. Let's find out how everything around us is so attractive. It might not be possible to study physics without knowing who this man is. Sir Isaac Newton had a massive influence on science in his time, especially the fields of mechanics, optics, and calculus. Among his many achievements, he formulated the 3 laws of motion that got my YouTube channel started. And yes, he's supposedly the man who is taught about gravity by a skydiving apple. What we now call the law of universal gravitation was first articulated in 1687, when Newton published his famous Principia texts. This law pulls together a few observations, which I will now outline. Firstly, any object with mass can exert a force on any other object with mass. We call this a gravitational force. For instance, the planet Earth exerts a gravitational force on you. This force is your weight. The size of a gravitational force, in newtons, depends on the amount of mass involved, which is measured in kilograms. Both of the interacting masses contribute. The size of the force is proportional to the product of the two masses, what you get when you multiply them together. Next, it was observed that the gravitational force between two masses gets weaker the further they are apart. Likewise, placing the masses closer together increases the gravitational force between them. It is not a linear relationship, but instead an inverse square one. Halving the distance increases the amount of force by 4 times. It changes exponentially with distance. Finally, it was clear that gravitational forces are only ever attractive. They always pull and never push. This is unusual because other familiar forces, such as electrostatic forces, can push or pull depending on the situation. I shall come back to this point later because it has far-reaching implications. It was up to Newton to combine these observations with data from astronomical studies and a few ingenious experiments. When he did so, he produced an equation that allows for the precise calculation of gravitational forces. Apart from a correction by Einstein, which is too small to worry about here, it hasn't changed much since Newton's time. The equation, as it appears in modern textbooks, looks like this. Capital F with a subscript G is the symbol used for gravitational force. M1 and M2 refer to the masses of the two objects that are pulling on each other. R is the distance between their centers of mass, and as you can see, it is being squared. Finally, the capital G is a constant that is needed to make both sides of this equation equal. It's an extremely small number, which reflects the fact that gravitational forces are actually relatively tiny, and you don't notice them on small scales. It takes a very heavy mass to generate noticeable forces, like a planet. Since you came looking for this video, chances are you're being asked to use Newton's equation in homework or test questions. I'd like to help out, so I'm now going to run through several example questions involving the law of universal gravitation. These will incorporate realistic data that you might receive in an exam. Of course, I will give you some time to answer each question yourself so you can have some practice. Are you ready to get started? Let's begin with the two most familiar astronomical bodies, the Earth and its moon. Each of their masses and the distance between them is known to a high degree of accuracy. The mass of the Earth is just under 6 times 10 to the power of 24 kilograms. The moon is 2 orders of magnitude lighter, but that's still an incredible mass. To stick with SI units, here is the average distance between their centers of mass in meters. Finally, this is the value of capital G, the gravitational constant. Using this data, and the equation we discussed, can you figure out the size of the gravitational force between Earth and its moon? Pause the video now and play it again when you have an answer. Here's my working for this question and the final answer rounded to 3 decimal places. If you got the same result, congratulations! If not, don't worry, that just means we should keep practicing. For the next question, let's replace the moon with the sun, the heaviest body in our solar system. Its immense gravity shaped the system over 4 billion years ago and has driven its development ever since. Now, let's find out exactly how strong that gravitational force is. Same as before, pause the video now while you give this calculation a try. This is what I came up with. It's worth pointing out that the force the Sun exerts on the Earth is the same size as the force exerted by the Earth on the Sun. This is a consequence of Newton's third law. Forces occur in equal but opposite pointing pairs. How about one more example? This time, let's take a look at the further reaches of the solar system, beyond the 8 major planets. Out here we find icy bodies like Pluto and its mysterious moon, Charon. Both of them contain less mass than Earth's moon, and they are relatively close together, which might make this calculation a little more manageable. Pause the video now and see if you can complete it by yourself. According to my efforts, this is the size of the gravitational force between Pluto and Charon. Well done for following this far. To finish off this video, I'd like to point out some interesting observations of our universe. As I said before, the force of gravity is always attractive. It pulls astronomical objects closer together. It is also considered to have an infinite range. This means that at any point within the universe, gravitational forces are possible, even if they are too small to detect. Putting these facts together presents a conundrum. Why is the universe we know able to exist? If gravity has infinite range, and acts to pull things closer together, then surely all matter in the universe should have collapsed in on itself by now. It should all be squashed up in a uniform ball, or something stranger, like the singularity at the center of a black hole. What we actually see is a universe full of variety, in which collections of matter are able to exist separately from each other, as galaxies, nebulae, stars, and planets. In fact, the universe overall is expanding over time, not collapsing under its own weight as we might expect. Clearly there are forces at play other than gravity, and they must be acting to push objects further apart. Physicists attribute these unknown forces to dark matter or dark energy, things that are barely understood but seem to make up a significant chunk of our universe. There is still so much to learn, but by understanding tools like the law of universal gravitation, we can now go forward confidently and tackle the deeper mysteries of physics. Thank you for watching this video. If you found it helpful, please leave a like and subscribe to my channel so you don't miss the next one. You can also post a comment below with any questions, criticisms, or requests for future topics. Bye for now, and good luck with your studies.